Okay, so this is
Hey, Dr. Savage, I had a real quick question.
okay.
I was curious about the format of the final.
Okay. So, yeah, we'll talk about that today too. So just hang tight for a sec, and I'll go through this exam, and then we'll talk a little bit about the final, which you may not remember from the start of class. We talked a little bit how that was going to work, but hopefully it's going to work out how I want it to work out. But yeah, that's a good question. So I will come back to that. Okay.
Perfect.
All right.
Thanks.
You bet. So like the other exams, you get one 3x5 inch card. I will be here looking, make sure it's not big. 3x5 inch. If you need a 3x5 inch card, you're welcome to stop by my office. Calculator, ruler, scale if you want one. 15 minutes, so in class. We'll get another classroom, so we have plenty of room to spread out. Oh no, I copied the wrong one. Yeah, we did a little more last year because we're a week short this year. Okay, I can't remember how to get on the box. All right, I'll just write it on the overhead. And note that I will, when I get back to my office, I'll post the official one. So essentially the homework from after, I think homework 19 or 20, I'm not exactly sure, but the things you're going to need to know for the exam. So we talked a little bit about pumps after the second exam, specifically pumps in parallel and series. Okay, which means that you'll need to know all of the basic things that you about pumps. You know, if you're going to be able to do them in parallel and series, you have to understand basic pump principles. So you were tested on pump principles. You could be tested on those again in a problem that asks you about pumps in parallel and pumps in series. In fact, there's probably a pretty good chance that you will probably have a pump in parallel, pump in series type question or questions. So this will include basic pump principles. Okay. You also need to know about the affinity laws. Or pumps in specific, I guess, variable speed pumps is a better way of putting this, variable speed. What are the affinity laws? How do you construct the graphs? How do you find the operating point for a pump that is running at a different speed than in its initial pump curve talked about? Okay. Then you're also going to need to know how to do, okay, let's see, pumps and parallels. Net positive suction head was on the last exam. So I think that's primarily the pump questions. But then we looked at adding pumps to a network. Okay. How pumps fit in network equations. And this could include converting a pump curve to an equation. Because if we're going to add a pump to our network, we have to be able to get it in equation form. All right. Okay, and then we started talking about population growth. Simple population growth. We didn't get very far into population growth. And we talked about water demands. Water demands include the annual average daily flow, the peak, let's see, the max day, max daily, peak hour. Okay. Now I obviously will supply any peaking factors that you may need. I don't expect you to have those memorized, but you'll be able to calculate all those. You should be able to calculate fire flows from the different methods. Okay. And then using your annual average daily flow, the peak daily, peak hourly, determine, and also include the population growth, determine the design flow for the network. Okay. But along with finding the design flow, you should be able to find the required storage. Given a time period. Okay. So we did an example of this in class, and I think you had one homework problem where you knew the design flow, and then you also knew the time of the fire flow, and you had to calculate then how much storage would be needed if you did like 1 day of storage in capacity. All right. And then from the water demands, we jumped over to open channel flow. So we talked about open channel. And we looked at Manning's equation and critical depth. For pipe flow. So we didn't expand that into open channel in the sense of, I gotta be careful because it is open channel. We didn't expand it into trapezoidal channels or ditches. It was purely just pipe flow. Okay, so you should be able to calculate that. And then from this, you should be able to calculate or compute the completely random. All right. So you should be able to compute things like the depth, the velocity, flow rate, the diameter for partial flow. Not only compute, but you should be able to size a pipe. Okay. That right there, I think, represents everything that we've covered since the second exam. Piece of cake, right?
Do you think you could post the homework solution?
Yeah, so I realize I'm a little slow as usual this whole semester, so I will try and get those posted by tonight. Assuming I don't get too many fires. If not tonight, first thing tomorrow morning. So, you know, I think there's 6 or 7 homeworks. I think 6. This is going to be pulled from. Obviously, you only have 50 minutes, so if I asked you to solve an open channel flow problem using the equations, I'd have to give you more time because the equations are kind of ugly. And it's not that they're very complex, they're just ugly. A lot of algebra. You should know how to use those curves that were given in the last homework. Partial flow curves, taking into account the changing Manning's N. All right. What?
Those equations in the book for the open channel flow, should those be on our note card or?
Put them on your note card. Yeah, but remember, it's only for circular channels.
With the curves, I noticed that the one that you made is slightly different than the one that's like just given in the problems. Like, why is that? And there's one.
Different in what way?
So like the homework we did, I can't remember exactly what the number was, like the depth was like 0.79. And if like the curve that was given right on the problem, it had the discharge like it crossed like directly at that point. And then the one you made was slightly like it was shifted, so it was less than 1, where the homework problem that we did was at 1, unless I messed something up. But
That's curious. I don't know. I haven't seen that, or no one's pointed that out. It's quite possible through the multiple printing and scanning of the one from the book that things have been distorted a little bit.
okay.
Is it just a little bit, or is it a lot?
It's enough that when we did like the percent differences, depending on which one you use, you'd be closer or further away. That's when I noticed it. It was not.
Yeah,
Unless, like I said, I could have messed something.
yeah, I'll have to take a look. The one I made, essentially what I did was I went into, I found the paper that the article or the book that has the design graph references for the changing Manning's N. So then I plotted up the different N values or for different depths. And then I went into Excel and I basically then recreated those graphs so I could simplify them a little bit because I wanted to show the difference in between if you had a variable N or if you had a fixed N value. And so I would think, assuming that they both use the same equations that they referenced and that I used, that they should be within, you know, the accuracy of a graph and how it gets distorted sometimes, or how you read it. But I don't know. I'll have to look at that. That's interesting. If that really is indeed, and it's more than just 1 or 2%.
I think it was. I don't think it was more than that. It was like looking at the one you gave us the other day. So if you have your like D over D full is like 0.79, that crosses the discharge line at basically 1. Is your like the bottom line, and then that one you gave us is probably like 9.5 or a little bit less.
9.5, that's big, that's 5% difference. That's,
So if you just looked at like the homework 26, it has both graphs on there, and that's,
oh, come on. I just told it I wanted to use Adobe. Where's Adobe? Right there, okay, do it, yeah, all right. Okay, so the discharge at 0.8 is a little over 1. Down here, and come on. 0.8 discharge is, wow, that is different. Oh wait, yeah, that is. There's a problem there.
so like I said, I just was,
Hmm.
I wasn't sure which one to use or like how.
Use the one I give you on the exam. I do not know. I wonder if for some reason I grabbed the wrong one, and this is not, this is the one without the fixed end. I mean, this is with the fixed end, but let's see, didn't I do that down here? Let's look at the fixed end. No, the fixed end's even worse. Huh. Yeah, that's too big of a difference. There's a mistake somewhere. So I'll have to look into that and see what's going on. Appreciate you catching that. So, but for the exam, use the one that I give you for the problem. But the concept here, if you understand the concept, then you'll be able to take any one. And
Yeah, like I said, I just noticed that when I think it was part 3, and the first problem was either use an equation or use that graph to find the percent differences.
I'm still back here. Oh, the fixed end comes close to 1. So I wonder if that's it, if this is fixed, but I thought this was always the one that with the variable end, because that's the principle I wanted to teach. And there would be 2% difference in that. Maybe 3%, but that goes over a little bit. I will look into that. Okay. All right, so now we're open for questions about concepts.
So the networks with pumps, when you're talking about like the positive HP versus negative HP with and against, that's for the direction of the pseudo loop, right?
It's the direction of a loop, not necessarily the pseudo loop.
Okay.
Because you could stick a pump inside your network, a booster pump. I mean, this is a real world thing. The pump is not always just located on the pseudo loop. It could be located on a regular loop. And so it depends on the direction of your loop, whether it's pseudo or a regular loop, on whether it's positive or negative. Okay. And it's like following the hydraulic grade line around.
Could we go over problem number 3 from homework 25?
Problem number 3, this is 26, right?
Yeah.
Okay, go back to 25 here. Problem number 3 being the 5.2.1.
Yeah.
Okay. Anyone have their book handy? I didn't bring my book.
I can grab mine.
Well, yeah, here. Thank you. All right. Oh, come on. Okay. 5.2.1, compute the critical depth in a 36-inch diameter culvert with a slope of 0.0016 for a discharge of 10 CFS. All right. So what we're given is we know that we have we're trying to find the critical depth. So the Froude number equals 1, as does the Froude number squared equals 1. Square 1, you get 1 squared, right? And the flow rate then is Q is equal to 10 CFS. The slope is 0.0016, and the diameter is 36 inches. And we want to find critical depth, which is usually denoted as Y sub C. Depth is Y, C represents critical, okay? So when we look at this, we know that the Froude number squared is equal to 1, and the Froude number squared is equal to the general equation Q squared times the top width divided by gravity times A cubed. Okay? So starting with what we know now, we know that the Froude number squared goes to 1. We know that Q squared goes to 10 CFS. And then from here, the rest of the way, what we need to know is what is the top width for a partially flow full pipe. So we're going to come back to that table that we referenced in chapter 5. Okay. So let's see, let me show you the whole thing right here. Okay, so the top width for a circular channel is going to be, we have one of two equations here, okay? And I don't know that it matters. I mean, if we stick the top one in here, then we're going to have to stick this bottom one in, and it's going to collapse down to this anyway. So I'm just going to go ahead and stick with that one. So I'm going to take each of these equations. I need the area, I need the top width, and that's it, right? So coming back over here, zooming out, that I know then that the top width is equal to 2 times the square root of y times d, the diameter, minus y. Okay. I know that the area is equal to 1/8 times sine, or theta, minus sine theta times d squared. And I also know that theta is equal to 2 times the inverse cosine of 1 minus 2y times, or divided by d, sorry. The inverse cosine of 1 minus 2y divided by d, okay? So now it's plug and chug. I put the top width up in there. I put the area over there. But before I put the area over there, I stick the value for theta in each of these terms and stick that in there, cube the whole thing. G is obviously the gravitational constant. And you'll see once I do that, the only unknowns in this equation is y. I have 3 y's right there. So I just have to solve that equation now for y. That's a big, long, ugly equation. And I would highly recommend that you use a solver on your calculator or Excel to solve that, because if you try and solve that by hand, you're likely to make a mistake. And quite honestly, it may not be solvable. It may not be implicitly solvable, but you could take a guess. Go ahead.
I say it took me 5 iterations doing it by hand.
Yeah. So this is where you use one of the tools that are available to you. And now, obviously, we can't cover open channel flow in a lot of detail in this class. To simplify our life, if you take open channel flow class, I will show you a graph. And so once again, stick it into a calculator or an Excel, spits it right out. It's beautiful. If you don't want to do that, there's a simple little graph. You calculate a couple of terms, come off to the curve, come over, and boom, you got it. So, you know, the old timers, before we had calculators and spreadsheets, they had ways of doing these as well, because not a lot of people want to grind through that algebra.
So in the exam, would we just have to like write the equation for it then?
Well, that's one thing I could ask you. I could ask you to write the equation and make it in terms of y. Yeah, if I wanted to make this thing one problem the whole test, you know.
Because
No.
I solved it on Excel, but I don't know.
Yeah, but you won't have Excel, yeah. So obviously, if I asked you something like that, I could say write the equation. Or I could find a scenario where things fall out really easily. If I gave you the depth and asked you to find theta, well, that'd be easy then, right? Because then you just come down to this equation right here. If you know the diameter and the depth, you find theta. So I can ask you parts. Or I could say, here's the depth in a 36 pipe that's flowing at a flow rate, or that's flowing at critical depth. What's the flow rate? Well, if you know the depth, you know the diameter, you can calculate the area, you can calculate all this stuff, and the top width, and now the unknown over here is Q, and that falls right out. So there's other things I can ask with this process that are doable within an exam time. Okay. So make sure you have those equations on your card.
And all those are in radians, correct?
Theta is always in radians, yes. Okay. Additional questions about this? If not, let's open it up then for other questions.
So the homework we just had last night, when like you had to find the flow rate and velocity with the figure and then versus the equation,
Mm-hmm.
what does it, because didn't we use the equation like in the examples in class? Didn't we use part of the manual equation with the figure, or was that a different thing? To find like the Q4 and then we use the graph to find Q and Q4?
Thank you, Lauren. I'm not sure I understand your question. Tell me again. So when we use Manning's equation to get Q full,
Yeah.
we can use Manning's equation to find any of the variables if we use this chart in the book to replace the area and the lettered perimeter.
So when it asks for the, I'm speaking about when it asks for just the equation, that's the equation in the book.
Just the equation would be the equation in the book with these parameters. What I'm not asking you to do as undergraduates is solve the equation for a variable Manning's n. If you use the equations, right now you use a fixed Manning's n. Because the variable one, that adds another set of equations. It's actually a set of equations. It's not a nice single equation across the whole pipe. It's kind of a couple of multiple equations depending upon your depth. Did that answer your question?
I think so.
If not, tell it to me in a slightly different way here. Let me see if I can better understand.
I think, so on the homework problem, the first problem, it said for part E or part A to solve for, was it Q?
Yeah.
Oh, yes,
Q
okay.
Using the graph, and then the second part asked to solve Q using the equation.
Okay, so now I
think her
understand.
question is like, because we
Yeah.
used, how we did it in class, we used the equation, like the Q full, to find.
Yeah.
Or Q from the graph.
Okay. So you always have to use the equation Q full to find, or V, the velocity, to find or to use that graph. And that's what it's based on. It's part of the dimensionless parameters. What I was trying to do in that third part there was to have you use the graph to solve it, and then use the equation. And the graph's supposed to have the variable n, and have you then use the equation using the fixed n to show you that there's a difference between the two. Did you guys come up with a difference? Okay. If you're shaking your head, if you came up with a difference, it's supposed to be a difference because the equation with these right here, with these values, and a fixed n should give you a different value than the graph unless you're doing a full pipe flow. Because full pipe flow is with a fixed Manning's n. I mean, it's one depth. Does that make sense? So that was my goal, was for you to look at it and say, wow, there's a difference here. Okay. All right, other questions?
Dr. Savage,
Yes.
can we quickly go over converting a pump curve to the equation?
Sure. So if we have a pump curve, and our goal is to fit an equation of the form that the head of the pump is equal to the shutoff head plus A times Q plus B times Q squared, noting that A and B can be negative. These are simply coefficients that help define this. So we've basically said this is the form that we want our pump curve to be. We can have other forms. There's other forms of a pump curve. You can actually have a 2-point pump curve, which H sub P is equal to H sub naught plus, I don't know, we'll call it D Q squared. It's a lot steeper of a curve than this here, okay? But this here is more accurate. So we want to take this pump curve and fit this form of the equation. And in order to do that, we have to find what is the shutoff head and what is these two variables. Or these two, they're not variables once we find them, they're constants. What are these coefficients that will give us this pump curve and it will match up here, okay? So the typical way is that we identify 3 points on our pump curve, usually the shutoff head, and then somewhere in the range or something that brackets the range of where we think the pump's going to operate. So if this is my system curve up through here, I'm probably going to pick a point here and a point here. Those would be 2 logical points, okay? So I'm going to come down here and I'm going to say for a given Q, and we can either do this in gallons per minute or in cubic feet per second, doesn't matter. Just make sure that whatever value you use, it matches up with the equations that you're going to stick it with. Now, because we're going to put this in an equation with a pipe network that is calculating in terms of cubic feet per second, I'm going to convert my pump curve to cubic feet per second. Okay, so I'm going to pick some flow rates here in gallons per minute, and you could do the conversion inside the curve too. I mean, but that, you know, it just gets a little messier. I don't know. I'm going to pick some nice round numbers here. I'm going to assume that this value right here is 450, and this one right here is 900 gallons per minute, just because, and this is 0, just because it makes the algebra easy. And then I go Q in terms of cubic feet per second. Well, this is going to be 0, this is going to be 1, this is going to be 2, essentially. Okay. As long as I don't get too far out into the decimals, because 448.5 gallons per minute equals 1 cubic feet per second. And then I'm going to find the head in terms of feet. So let's say that this is 120, and we'll say this is 100, and this one is 85. So I'm going to say 120, 100, and 85. Okay. So now I can essentially find, I can write 3 equations. Okay. So my equations then, equation 1 is going to be the head of the pump is equal to 120 plus A times 0 plus B times 0 squared. My second equation, the head of the pump, is going to equal 120 plus A times 1 plus B times 2 squared. And my third equation, the head of the pump, is going to be equal to 120 plus A times 2 plus B times 2 squared. Now you'll note that the flow rate is a known value here. So once that's squared, this is 3 linear equations. That's all this is. It's 3 linear equations. 3 equations of x plus y plus z equals, some constant. And you guys know how to solve linear equations. So now all we have to do, whoops, I made a mistake. One mistake here, didn't I? I'm moving ahead too fast. Darn it. I hate when I do this. This should be h sub naught. This should be 120. This should be 100. This should be h sub naught. This should be 85. And this should be h sub naught. Because the 3 variables that we're trying to solve for, we want to solve for h sub naught, A, and B.
You also put on the second equation, you put B2
Oh.
squared.
Thank you. Yeah, that should be 1 squared, yeah. So I stick all my flows in each one of these. So the first flow is 0, the second flow is 1, third flow is 2. Now, we already know what the shell-off head is because at 0, 0, A and B go out and h naught is equal to 120, right? So, I mean, that makes life easy. But we can, in this form, we can now write a matrix. Coefficient out in front of h sub naught is 1. So I'll put my 3 in there. And then the coefficient out in front of A is 0. Coefficient in front of B is 0. The coefficient in the second equation is 1. In front of B, it's 1 because 1 squared is 1. The coefficient in front of A for the third equation is 2. And in front of B, it is 4. That creates my coefficient matrix. My solution vector then is going to be h sub naught, A, and B. And this is going to equal then my B vector of 120, 100, and 85. And if I solve that system, okay, I will get then the coefficients for, I'll get the values, sorry. I'll get the values for h sub naught, A, and B. And the one for h sub naught better come out to be 1. Sorry. Better come out to be 120 in this case, right? Because I already know what that answer is. So if I plug this into my matrix to solve it, now you could solve this by back substitution too. First equation's already solved. So now I can turn this, I can convert all these to 120. And now I have 2 equations, 2 unknowns. And so I can sit and solve those too. A little bit longer to do it by hand than if you use your calculator to solve a matrix. Okay. Questions on that? Okay. Other questions? Oh, geez. Okay, we got 5 minutes, so let me talk about the font.
Affinity laws.
Can I do what?
Can you talk more about affinity laws? Affinity laws.
Laws? So the affinity laws, so I'm not gonna have time really, so schedule a time with me, either in my office or via Zoom, and I'll be happy to go through those, okay?
Uh.
5 minutes here, and I want to talk about the final exam. I did send out an email. So. I don't want Zoom instructions, I want Gmail. So the goal for the final exam is a project. Okay? And did I not send, did you guys get an email from me right before class? Yeah. Oh, okay, there we go. Ah, geez, come on. All right. So we want to use Bentley's software, and this was sent because we have a stat account as well. But Bentley is a company that has, geez, I don't know how many software programs they have now tied to the civil/engineering community. It's huge. I don't even know what most of them do, but they have STAAD, they have Bridge, they have Form, and if I had my laptop hooked up, well, here's 50 applications. We can bring this up. Comes up. Anyway, what I want to do is briefly introduce you to WaterCAD. So it is a professional program, probably, in my opinion, the best one, or it was the best one, back when Haystad started it. I haven't kept up with the field too much there, but I'm assuming it's still kind of the leader, even though AutoCAD has tried to incorporate through Civil 3D water networks into their software as well. And I may switch to that, I don't know. But Bentley is the company that puts out MicroStation. So if you're not aware, MicroStation is a competitor with AutoCAD. And last time I looked, it's kind of interesting, 49 out of the 50 DOTs across the country use MicroStation. If you are a consulting engineer, you probably are more likely to use AutoCAD, unless you do work with the DOT, because they want all their files in MicroStation. MicroStation has Inroads, which is a really good program for bringing in topographical surveys and designing roads and doing the cuts and the fills. It's a beautiful program for doing that kind of thing and also doing then subdivisions, but Civil 3D does that as well. So two competitors, but Bentley has WaterCAD, and I do not know why this is not coming up, but they also, like I said, STAAD, all these different programs, and we have access to them for about another week and a half to all the different programs. And then they're going to change the style of the license. And I'm not sure, I'm not even sure how that's going to work. But if you want to download some of these other licenses, so for some reason it's just not working, but you can do it. So what you do is you go to Bentley right here, the student server, and you need this code right there, and you're going to have to create an individual account. And once you get that individual account, you can go in and download any one of their software packages. Well, here, we can look at it from here. download software. And then you're gonna say I'm gonna have to log in. Let's see if I can log in really fast. I installed this on my laptop this morning. And I was looking at their different training packages, and from what I could find so far, I probably spent, I don't know, an hour and a half looking this morning. It wasn't that impressed, but okay. So really quickly, I know we're running out of time here. Here's their product line. Civil design, bridge analysis, blah, blah, blah. Come down to here to hydraulics and hydrology. And the brand is Open Flows. It used to be Haystad, now they've changed it to Open Flows. I apply that. They've got Culvert Master, Civil Storm, Open Flows. So hydrology software, hammers for transients, Open Flows Sewer CAD, Sewer Gems. So WaterCAD or Water Gems, it doesn't matter to me. Either one of these, you get the software, you have that code, you can download it to your home computer, to your laptop. You can get any of the other ones, and I think they work for a year. At the end of November or into December, they're going to switch over to what they call the select server, where we have to pay for the individual. Right now, it's just open for any of these, but then they're going to switch it over to where we have to pay for individual softwares. They tell us that it's supposed to save us money. I don't think it's going to do that. But we use your student lab fees for doing this. So grab any software you say you want to get. They're supposed to have a method up here somewhere, assets or with training videos. That's not assets. You can search for, well, come back to home. Where did I find those this morning? Project Insights, find training over here. You can watch videos, you can download. The WaterCAD, not what I wanted here. The WaterCAD one is not that great. But so what I'm going to do is I'm going to give you a project, and I will share with you on Monday. We'll go through how to set up on Monday, go through the program. So if you have it installed on your laptop, you might want to bring it, because I'm going to have mine. I got to figure out how to get my laptop hooked up to this machine, but and I'll kind of show you how to set up. I may also do another video on myself to kind of give you additional information. And then I'm going to give you a simple pipe network system for you to go in, figure some things out, and your final then is going to be a project. Okay. And that way you don't have to worry about a final exam. You just got to do a project. It's not looking to be a big project. There will be a write-up, a couple of pages, 2-3 pages, and that'll be it.
Do you know when it'll be due?
It'll be due towards, I don't know when our final's scheduled for. Monday. Okay, we'll push it farther back in the week, maybe like Thursday night or something, because I'd kind of like to get them all graded and stuff. So I'll make an executive decision Thursday at midnight. So that'll give me Friday to start grading, Friday and the weekend and Monday to grade, and get your grades entered by Tuesday. Okay, I'll give you plenty of time to do it, and you get all your other finals out of the way. Well, most of them. I don't know if you have any scheduled for Friday. Have a great day, and we'll see you on Friday.